Okay, we're looking at the second challenge here. This is the 4-step sequencer. So what we're asking you to do here, this is very similar to the general flow of the batch mixers. So asking you to create a 4-step sequencer that keeps track of what step you are at in the sequence. So this is pretty much the way that we've been doing the batch mixers, where you have like a fill and then maybe a second fill and a heat and a mix and then a drain cycle all in there that all happen in that order, and you need to kind of step between each of those sequences all in order. So we're asking you to create basically that sequencer here. So what we want you to do, use some type of start, stop, enable, seal logic to start the whole sequence. Each step is going to run for about 3 seconds. So basically we're going to make a timer that's going to dictate the process when it's actually finished. In our simulations we've been doing in the lab, this might be a timer, it might be a level switch, it might be something else, but some type of event that triggers that you've actually completed that stage of the process. For this one here, we're just going to do a 3-second timer for each one. We're going to use some seal logic to record when each step is complete. So when a step completes, we're actually going to create a complete bit, and we're going to seal that in. Once the 4th step completes, we've got to the end of our sequence, we're going to reset everything. And then in our simulation, we're going to tie each of these steps to a light so we can actually see what is happening as well. So that is the challenge. Here, I already have the logic done, so I'm not going to key it all in because it's a little bit lengthy. Now, the only reason there's a lot of logic is because there's a bunch of steps, but what you will see here is all the steps are essentially the same. It's the same structure, the same logic. The only thing that changes is the addresses each time because we can't reuse addresses. So looking through what we're actually doing here, the first thing we asked for was use start, stop, enable, seal logic to start the sequence. So this is going to be pretty common. We have a start button, a stop button, an enable button, and then an enable internal bit or a real output, either one, and we're using that to seal this in. So basically that gives us control over actually run here. Don't download and run. So that actually gives us control over this enable bit. So we can start, we can stop, start, stop. And you can see I'm actually using this enable as an output, which I'm tying to this first light here. You can see, so when I'm enabled, that first light actually comes on. So that's my enable circuit. And then each step that I have now basically looks like these 2 lines of logic right here. So I have some type of action going on. In this case, we are basically running a timer. And we say we're going to run this timer if I am enabled and if I have not completed this step yet. So this action is going to take place as long as I'm enabled and as long as this step has not completed. Okay, so that's what's going on right here. As long as these are true, I'm going to run this timer. Now, once this timer finishes, I am going to lock in a seal that says that step 1 has completed. I seal that in. The only thing that breaks this seal is this bit here that is called process complete, and this is basically going to be the summary of all of my steps being completed. Okay, so you'll start to notice that each of these steps is going to look pretty much identical to this. Now the only difference, so this is step 1, the only difference here when we get to step 2, this and this essentially the same, but now I say I run this step if step 1 has completed, step 2 has not completed. That's what kind of indicates to me that I'm in step 2 right now. is that step 1 has completed, step 2 has not completed. This is how I avoid multiple steps from trying to think that they are supposed to run at the same time. This is going to control and say if I have 1 has completed, 2 has not completed, I know that I'm actually in step 2 right now. I'm not in step 4, I'm not in step 3, I can only be in step 2 for these things to be this way. And once again, once this timer is done, I seal in a bit that says step 2 is completed. I reset it when my process is complete. Step 3, same thing. Step 1 is complete, step 2 is complete, step 3 is not complete. Then I run my timer. Once the timer is done, I lock in and say step 3 is complete. I reset this when my process is complete. Step 4, exact same thing, same pattern. Be down here. And then the very last thing that I do is I say if step 1 is complete, and step 2 is complete, and step 3 is complete, and step 4 is complete, then my process is complete. So once everything finishes, I've got all the way step 1, step 2, step 3, step 4. I'm going to turn this bit on, and what's going to happen here, once this comes on, this will break all my seals. All of these bits will then go off. So you'll probably never actually see this come on, because basically when we run this, you'll see this lights up, then this lights up, and this lights up, and then as soon as this lights up, that means this comes on, and it's actually going to kill all this stuff, and that will take us back to the beginning. So let's try running this sequence, and then you'll also see that these are all tied to lights as well. So these, instead of using I could use internal bits here, I've decided to use lights instead, just to make the programming a little bit simpler. But what's going to happen here, so this is the enable bit, step 1, step 2, step 3, and then step 4 will just blip on and then go off. Then I go back to step 1 again, step 2, step 3, step 4, and then blip off back up to the top. And if we watch over here, I have step 1 completing, step 2 completing, step 3 completing. As soon as step 4 completes, process complete will come on. That'll reset everything. So if we watch through the logic here, again we're going to see this time, then this will lock in, then this will time, then this will lock in, then this will time, then this will lock in, then this will time, and then we reset everything. Okay, so this is the general form that we can use for a step sequencer like we're using in the batch mixer. So the only differences between this and the way the batch mixer would run would be we'd probably break each of these steps up into its own subroutine just to make it easier to look at, so you don't have a program you need to scroll through. Each subroutine should only be a couple of lines long. And then this line here where we're running our timer, this won't necessarily be a timer. It could be are we actually doing in that step? Are we running a pump? Are we running a motor? And then what indicates to us that we finished our step? What actually makes us complete? Is it a time value? Is it a level switch? Is it something else that indicates that we've actually completed? And that is what would have to go in here. Okay, so that is the basic form of the step sequencer. The other thing we could do, if we wanted this to only run once we hit process complete, we should be able to put that process complete in here to break our enable as well. I should be able to actually change this logic right now and just say as long as we are not process complete. So what this will do now is that this will break our enable circuit when we hit process complete again, and this sequence should only cycle once. So now we're running, so now not only will it reset all these seals, it'll also reset our enable seal. Basically, it's like pushing the stop button at the end of the sequence, so you can see that shut everything down, and then we had to push this button to start again. that will run us through again. We're basically running one batch, much like the advanced batch mixer lab where we were counting how many batches we ran. You could put the counter done bit there. This is basically the same operation as if we were to hit the stop button as soon as we finished our last process. And that is the step counter.